Okay, so today we have with us Dr. Ligia Cavani. Dr. Cavani is originally from Brazil, where she received her Bachelor of Science in Animal Science, Masters of Science, and PhD from Sao Paulo State University. Dr. Cavani is now a postdoctoral research associate at the Department of Animal and Dairy Sciences at the University of Wisconsin-Madison, working with Dr. Francisco Panagaricano and Dr. Kent Weigel. Her research has included quantitative genetics, the development of new phenotypes using high-throughput data sets, genomic prediction, and gene mapping in dairy cattle. And currently her focus has been on feed efficiency in Holstein cows. So thank you for joining us, Dr. Cavani. I'll give the floor over to you.
Thank you very much for the introduction, and thank you for the invitation. I'm really happy to be here and share part of the work that we have been doing here at University of Wisconsin-Madison. And also I'm really happy today because to talk about feed efficiency that I started work, I think 2 years ago, and it's for me, it's really interesting and I like a lot to work with this topic. So this started. So I would like to start asking a question. What's the importance of feed efficiency? So I'm pretty sure that everybody knows that this is one of the most important traits in dairy and other species too. But I would like to highlight these two topics, that is costs and environmental impacts. So the feed represents more than 50% of the total production cost. So even with small changes or in the feed, in the total feed that we provide, so the impact it's big, right? And also the second thing is the environmental impact. So if you have cows that are more efficient, so we need less land, and consequently we have a
Sorry, Ligia. If this is Filippo, I cannot see your slides. I don't know if I'm the only one, but I see a blank screen.
Really?
Yeah, I cannot see either.
It's coming up for me. I just see the title slide, I guess.
We see a gray screen. That's it.
So let's see if I can change it.
Yeah, maybe kind of go out and try to come back in. Sharing, unshare, and then share again.
Okay, let's try again. How about now? Let's see.
That's good.
Yeah, I can see it now.
Here
Thanks,
we
Ligia.
Tire, like there's a picture, you can see it?
Yeah.
Okay, perfect.
Thank you.
So, okay, come back talking about the importance of the feed efficiency traits. So I think I stopped here in the impact, that's the, let me do something. Oh. There we go. The environmental impacts. So then if you can identify the cows that are more efficient, so then less land is needed, and then consequently we have a reduction of the green gas emissions, for example, methane emission, that it's huge nowadays, right? So I would like to show and to present a successful story that is the change in milk yield in the last 60 years. So in this graph, you can see the milk yield, and through the years, what's the trend was like a huge impact, a huge change. And the thing is that this change, this improvement, is of course due to management and everything but we have almost 6% due to genetics. And why this is so important? Well, the genetic, it's really important because the gains that we have through the genetic selection, they are cumulative and also permanent. So thinking about that we have been selecting for many traits through those years, and the impact is huge for the dairy production in general. So we can think that we can do the same for feed efficiency, right? And actually, this this production of this increase of milk production is also indirect. We are indirectly increase or improve the feed efficiency because of a dilution of energy the maintenance of those cows. But is an indirectly improvement, which you can do a lot. But the question is, and maybe it's the quick question for us that work with feed efficiency, is how do we measure feed efficiency? There are different ways, but residual feed intake, that's the measure, had been used a lot. And the trait is, it's defined as observed intake minus predict intake. So in this plot here, we can see, imagine at those, each dot is a cow, for example. And then we have here the observed intake, and then here in the axis, we have the predict intake, what we expect that she will eat, right? So then let's take an example of this cow here. So we predict, we expect that this cow will eat 18 kilos, but actually she ate more, right? So then she's less efficient. And because the residual feed intake that was observed minus prediction, so she has a positive residual feed intake, and that means for us less efficient cow. But the opposite happened of those cows here in this area. So for example, this cow here, we expect or we predict that she will eat around 19, but actually she ate around 13. So she has a negative residual intake, that means more efficient cow. But maybe the point here for this kind of phenotype is how we predict the intake, right? It's not an easy thing. So this is the equation that we have been using. So first thing we do by week, that's seems pretty efficient way to do it. So the dry matter intake is function of many factors, right? So we can say that it's a function of days in milk, the lactation number. These in blue are the three energy sinks. That means the milk energy, the metabolic body weight, and the change in body weight. And also we need to compare those cows at the same cohort. And the week, the data that we're collecting, the week that we're collecting the data. So the dry matter intake is a function of everything. And the residual part of this equation is actually our residual feed intake. That's what we observe minus that we predict. So, like I said, the genetic selection is a powerful tool to improve production or to improve any traits that you want, and feed efficiency the same. And we can use it, right? But look in this equation here, we can see that's not an easy phenotype to measure. And for example, we need intakes, individual intakes. This is not easy and it's not cheap to do. But with the genomic selection, that's an important tool that is basically we can create a reference population that we have all this information that we collect for feed intake, for example, in research farm at university. And we have also one more source of information, that's the genotype data. We have markers information. So actually, we don't need a huge amount of data, and we can create our reference population with all this information, create our equation, build in our equation, and then predict the PTAs or the breeding values for the entire population, even with there is animals that doesn't have phenotype yet. So this is really powerful, and here at the United States, they are creating the reference population for to have this genomic PTAs. Basically, the collection of the data is at 5 research stations. So Michigan, here at UW, Iowa State, Florida, and USDA. And there's some difference between the research stations, but we collect feed intake daily. We have also milk production daily, milk composition 4 times a week. And we have also information of body weight that's are essential to have the residual feed intake phenotypes. This is once we have some data, it's once a week. Some data we have just we have at the beginning, at the middle, and at the end of the trial, but we can predict the body weight easily when I have this kind of data set that we have been doing this and it works fine. We also have different systems, and we have Incentec gates to collect those feed intake. We have Tystal, and we have also Callan gates. And the reference population is around 7,000 cows. So we have a lot of data. Another question that's important to implement genetic selection or genomic selection, if there is variance, genetic variance on feed efficiency, and this table will show yes, there is. So let's look just the residual feed intake here. So it's 16%. It's a good number, so we can have a good impact on selection with the heritability of 16%. We also have all the traits that compound the residual feed intake also with high heritability. That's good. So I show you that to calculate or to get the residual feed intake phenotype is not so simple. It's a regression model. So, and one of the things that we like to do here, and we study, kind of play a little bit with this equation and to see if there is an impact on how you calculate the residual feed intake on the re-rank of the animals or whatever. So this is one question that we would like to, we answered, that this is the paper that was published this year. So there is difference across lactation. So for that, we had 72,000 weekly records of residual feed intake. We use the entire data set, so the 5 research farms that we have from 2007 to 2021. And we had almost 6,000 hosting cows. So then we just consider the 3 lactation or parity. So then I have this amount of cow in parity or lactation 1, this amount of in parity 2, and of course I have less cow in parity 3. And how we answered the question and how we analyze the impact of residual feed intake, how it calculates across lactation. We did it in 2 ways. First, we look the phenotype association. So the way that I calculate or the way that I consider lactation in the residual feed intake model has an impact on the phenotype or not. So for that, we use this first model, that's a constant model. So it's the same that the classic one. And the second model, the lactation number was nested within days in milk, and the 3 energy sinks: milk energy, metabolic body weight, and changing body weight. The other thing that we did was actually consider different traits for residual feed intake for lactation 1, residual feed intake for lactation 2, and residual feed intake for lactation 3. So then we subset the data and then calculate the residual feed intake for each lactation. So then, of course, in this case, lactation will be just constant, right? The results of these two methods that we use, first, the phenotypic association. So here in this graph showing the phenotypes that we use using the traditional model, and here the nested model. As you can see here, there's no re-rank, so there's no impact. We can use both models. Of course, if you want to study more about what's the difference within lactation for milk, energy, or whatever, it's good to we can have more information for the second model. But for us, the phenotype doesn't change. For the second part of this study about genetic correlation, so then the genetic correlation is pretty high, as you can see here. So there is no difference between parity 1 and parity 2. High also for lactation 2 or parity 2 and parity 3. And also we have a small number here, but even high, 0.79, the correlation between residual feed intake in parity 1 and parity 3. So it's high, so maybe there is impact of the number of records, because I have less records in lactation 3, but even though it seems that it's fine, there is no such a huge impact, right? Also, what we did is to look the sires, the breeding values of the sires. If there is re-rank, there is some change when we have just parity 1 and then parity 2 and parity 3. In this case, the first graph, it's comparing residual feed intake in parity 1 and residual feed intake in parity 2. So again, almost the same. For parity 1 and parity 3, we have 0.91, the correlation. And for parity 2 and parity 3, 0.92. So then again, it seems that the impact is not that big. So then it's fine. We can use the same model, at least for now, right? Okay, but we know that there are some cows that need less feed than others, and they have similar body weight, for example, and meat production. And why is that? Why this happen? So there are many factors. There are factors that I didn't put here in the list, but there are like factors that we even don't know yet. There are many things that we still don't know. But I listed here some factors that contribute of this difference of feed efficiency in dairy. So we have difference in feeding behavior, digestibility, rumen microbiome, metabolism, physical activity, thermoregulation, and also we can say consistent of production, milk production, or dry matter intake. That this is related with resilience. So I will be focused on feeding behavior first and consistent, that are the things that we are working on here in our group. So another thing, so of course, all these factors and many factors that we still don't know, or it's not here on this list, it's important to understand better, right, the feed efficiency, biology or whatever, but also it's important since that we saw that it's not an easy phenotype is not so simple to get residual feed intake. So we can actually study indicator traits for feed efficiency. So we are doing genomic selection, and it's working, right? It's impressive, but even though the cost of phenotypes is high, and also it's difficult to implement in commercial farms, so we have a limitation of number of phenotypes. Even with genomic selection, we have impact on accuracy of the predictions when we use this kind of tool. And we need more and more phenotypes, so this keep going. So study or find some traits that can be an indicator, it's pretty important. And then we study feeding behavior, trying to see if can be used and if it's associated with feeding efficiency and can be used as indicator trait for feed efficiency. So then we use 1,300 lactating hosting cows from 31 experiments here at UW and from 2009 to 2020. We have a huge number of data set. Like I said before, we have this kind of system here at our farm. So this is Insetec Gates. So this kind of system can provide us a huge amount of data. So we have like 24 hours of data and measure the time that the cow enter the cow, the time that the cow leave the feed bank, how long she spent there, and of course the amount of food, everything. So with this data, we calculate some feeding behavior traits that are listed here. So then we have number of feeder visits, duration of each visit, total duration per day, intake per visit, and also feeding rate. As you can see here, we did as visit, just a single visit, and we also consider as meal, that basically is a group of visits. For the genetic analysis, we use this model. I put here just once because it's the kind of model that we use here for the genetic analysis, heritability, repeatability, and correlations. So then we use as fixed lactation and this in milk. We use a cohort that's a group of trial treatment because we are using this kind of data set as random. We also, of course, additive genetic effect, and because here I had daily records, and also I did the same but consider as weekly records, I have also the permanent environmental effects. Just one observation here. So for residual feed intake, for example, heritability, we don't have those effects, right? Because we already consider those at the first step, that is the phenotype, the residual feed intake phenotype. Just cannot count twice. Here in this table, we can see some data of our cows here, so the feeding behavior. So on average, a cow visits the bank per day almost 36 times. So each visit is around 7 minutes. What else? The cow eats on average 900 grams of dry matter intake. And the feeding rate, that's the kilos of dry matter per minute, was on average 0.150. So then we calculate the heritability to ask the first question: the feeding behavior are heritable and repeatable across days? So that then it is, right? So the heritability, we have around 16%, have higher heritability for feeding rate per meal, that was 23%. Also, quite often repeatable across days, right? This is daily, feeding behavior daily. So mainly for a number of visits per day, quite often repeatable. That's really important. And also, like I said, we did the same, but weekly, and then we calculate the heritability again and repeatability, and then we observe an increase of heritability estimates that is expected because we decrease a noise maybe on the daily data. So then the feeding behavior traits are quite repeatable and repeatable across weeks. So we can implement selection here and with this heritability and with success. And in this figure we can see the genetic correlation among the feeding behavioral traits. So here we have the genetic correlation, and here actually the phenotypic correlation, but focus just the genetic correlation. As we expect, almost we have high genetic correlation among feeding behavior, of course, number of visits, for example, and duration. They have a high negative correlation, right? The same, the intake per visit and the number of visits. We expect that one thing that's important for us is to look at the dry matter intake. So again, this is daily. So of course, the high genetic correlation are with the traits that we include dry matter intake to get, right? So then intake per visit, for example, intake per meal, that's a higher amount. But it's cool, for example, for feeding rate to have high and genetic correlation. So the final question, and maybe the most important one for this paper, was what's the association between feeding behavior and feed efficiency? Can I use feeding behavior as an indicator of feed efficiency in dairy? So this, so here I have efficiency traits that I consider those that I consider to in the model for residual feed intake, and here are all the feed behavior traits. So we have high genetic correlations between feeding rate and residual feed intake, so around 0.15. This means that a cow that eats in a slow rate, she is more efficient. We have some interesting relations also. For example, the total duration. We have high correlation with secreted milk energy, for example, and around 0.20 with residual feed intake. So yes, feeding behavior can be an indicator trait of feed efficiency. So the second thing that I want to discuss, this is the new thing that we're doing here, at least the project that I'm leading, is the consistent off-dry matter intake. So there is this general concept of resilience that we can say that's the capacity to bouncing back to normal function after a perturbation, or maintain specified function in the face of change or stress. Well, we know that different farms, different environments, we have a lot of things going on and a lot of perturbation of factors that can be a stress for the cow. And the thing is how the cow responds on that. She's able to keep in production without any chance, or there is a huge impact. So the goal is actually trying to identify those. In this work, we're working with dry matter intake. And basically the first step is to study the consistent of dry matter intake. If it's the consistent can be used as a resilient term, right? but we just started. There are like many things to do. So just to illustrate, for example, here we have 2 cows. So this is the kind of data that we have. So then we can do a lot of things, right? So then here we have the day of the trial. So then we have short trials. And here we have the dry matter intake. We have example of 2 cows in this graph. So if you look this graph without any more information, we can see, I guess, that this cow in red is more consistent in terms of dry matter intake than the blue one, right? And also we can say that there is less variation of dry matter intake for the cow that's represented in red compared to the cow that's represented in blue. So, okay, we can say that maybe, but how can I measure? How can I have a number, a phenotype, and do all the analysis? So, well, we are working with 6,300 cows. We have the period of each trial or experiment. It's from, we have a minimum of 27 days and a maximum of 150 days, but on average you have short trials, it's like around 4 days. So then we have amount of dry matter intake record. So then we are working with this data. So to get the phenotype for a consistent of dry matter intake, it's basically 4 steps. And this is, we are doing within cow for each cow. So first we estimate the expected daily dry matter intake for each cow. Second, we calculated the deviation of expect and observed daily dry matter intake for each cow again. So then after that, we calculate the variance of those deviations. And the first step is just to transform as log, just because of the normality of the phenotype. So these are the steps to get the phenotypes for consistent of dry matter intake that we have been using. But actually for the step 1, for example, how can we estimate the dry matter intake, like without any perturbation or any stress factor? So we are using 4 models to get the expected daily dry matter intake. So here is an example of each model that we are using to get the expected daily dry matter intake. It's an example of 1 cow. This cow is an average cow, so there is not much variation as we observed here. So then we use first, because I mean we have a short period, right, of the trial. It's not too long. So then we was thinking like we can use just the cow average as an information. So this is a constant model. So then we use the quantile regression. We use the quadratic and cubic, the 2 models. And also we use this Loess regression, that's a non-parametrical model, and we use the 2 different spans, that's the 0.7 and 0.5, that it's more related with the smooth of the curve. And as you can see here, for this cow, it seems that there's no difference, right, of those models. But when we have a cow with this behavior, for example, for dry matter intake, maybe there is an impact. Maybe using just the cow average is not enough or is not good to predict the dry matter intake. And it seems that quantile regression doesn't matter if I use cubic or quadratic. And Loess, it's also, it seems for cows that is kind of extreme in the variation, in terms of variation of dry matter intake. Maybe it's better to use. So then the first question is, are consistent traits heritable? Another thing that I forgot to say, we also did the same, exactly the same models for variance consistent of milk traits. Our focus in this project is consistent in dry matter intake, but we also wanted to see if there is association between consistent in dry matter intake and consistent in milk. And because we wanted to compare the same thing, we use the same model. So then, yes, the heritability was 0.11, and here we have 0.4, 0.14, but it's quite similar among models. That's not such difference, right? Another thing that we want answer, so this part of getting the expected value for dry matter intake, we use different models. So which one is better? It's kind of hard to tell, because if you use like measures, metrics for models, is not so right for this kind of project. Because, for example, for low-S regression, if you use a perfect model with a smaller error, you'll be just copying the data, and we don't want to copy the data, right? So we calculated here the genetic correlation. Yes, as you can see, that's really good for, at least for us, because there is no difference. We have just a smaller correlation here when you use just the average of the cow and when we use the low-S regression model. But I mean, the simplest model that's just the average is working. I mean, there's no difference, right? And what's the association between consistent in dry matter intake and consistent of milk? So this, we have the genetic correlation in this table here. So then we have actually high correlation. So then it seems that if you select for consistent in dry matter intake, we also has an impact in consistent in milk. That makes sense, right? Another thing that is really important for us is to see if there is association between consistent of dry matter intake and feed efficiency. So in this table we have here, this part are the log variance of dry matter intake, the traits that we use for consistent using different models. And here we have the feed efficiency traits. And it's really interesting because we have a positive correlation with residual feed intake. That means that cows that are less consistent are also less efficient. Okay, but how about other traits, right? So here in this table, what we did, we did the correlation, the Spearman's correlations with the sire's PTAs. So then here we have the columns. Again, the consistent traits of dry matter intake, that's our focus. And here we have the traits on national evaluation. We have production traits, longevity, health, reproductive traits, and also feed efficiency. So let's start here with feed efficiency. So again, we have a positive correlation with residual feed intake. And for feed safe, it's a feed efficiency trait too. It's a combination of body weight composite. So it's the interpretation is the opposite. So this means again that cows that are less consistent, there are a lot of variation of dry matter intake, those cows are less efficient. For production, we expect actually we have some positive correlation with production. So then the cows that are more consistent, there are a lot of variation, produce a little more, but they're not efficient. it seems at least. Not big correlation with longevity, not big correlation with healthy, that's good, and even not important correlation with repro, just conception rate for heifer here, right? So then it's also a correlation that tells us that we have less conception rate for cows that are not consistent. But another thing that we really are interested in, there are a lot of next steps on this project, but is actually trying to identify or the probability that something happened at the day. So, for example, in this graph here, we have an example of a cow. In blue is her dry matter intake, and in red is the milk production per day. So it's clear, looking this graph, that maybe something happened. We don't know what happened in this day here, 44, maybe here, right? And then she starts decreasing the intake, and then after that, decrease the milk production. So we are interested of course, we cannot look cow by cow. We have a huge data set, and also this is not our goal, but try to find a method that we can see what's the probability that this happened. And if you have a high probability, like in this graph, that something happened, and then we see across days, not across cows anymore, what's the difference between cows? So this cow here, this example, so there is a huge impact on her production, but maybe another cow, there is no impact, so she'll be like producing the same, or not a huge impact like this one. So this is our goal, that probably you have been working soon. And then also we can tell that this cow is less resilient or more resilient, and finally create a phenotype for that. Our message, so first, feed deficiency, it is an economically relevant trait. Residual feed intake, that's the most trait that we use for feed deficiency, is heritable. So the genetic selection can be effectively improve dairy cow feed deficiency. Also, we saw that residual feed intake is repeatable within lactation and is highly correlated across lactation. That's also good. And talking about the feeding behavior traits, we can say that they are heritable and repeatable across days and across weeks. So they are genetically correlated with feed deficiency traits, and mainly, I mean, the important one was feeding rate. So cows that eat slowly may be more efficient. So then they can be used as an indicator for feed efficiency in dairy. And for the last part, the consistent of dry matter intake is heritable. They are genetically correlated with feed efficiency traits, and maybe can be used as an indicator of resilience. And it seems the way that we estimate or we calculate the phenotype for consistent of dry matter intake doesn't matter much, doesn't change. That I would like to thank you, my group here, Kent Weigel, Francisco, and all the professors, students, postdoc that are involved at feed efficiency here at UW. I would like to thank you also the Dairy Innovation Hub, the USDA NIFA, FFR, and the CDC. Thank you.
Great, thank you, Dr. Cavani. If anyone has any questions, feel free to raise your hands. I did notice there was a question in the chat from John. Maybe I'll start with those. So for his first question, your prediction of RFI does not include a measure of body composition, for example, ultrasound back fat or rump fat, which is also an energy sink. So how important is this to your calculation of RFI?
Yeah, good question. For these models, for this project that I'm working on, we didn't consider that, but I assume that's important. I don't know the impact of this, but we use for body weight just the two measures, that is the changing body weight and metabolic body weight. That's the body weight of the power of 0.75. But yeah, maybe there is impact.
Okay, and a second trait, I think this was with regards to your for your feeding behavior traits. How do you define a meal?
Yes, we use a model that's the actually a mixture normal model. So then with this model, we could see basically two separate normal distribution, and then we could estimate the threshold that because one distribution is about within meal, and the other one is the separate. So then this threshold that's between the two normal models was, I think, 26 minutes. So then all the visit that is within 26 minutes, it was grouped as meal.
Great,
and also we did for all. We didn't do for each cow. What we did first was to see the impact if I use lactation 1, 2, and 3, but we got almost the same number, 26 minutes. So then we consider 26 minutes for everybody.
And Christine, go ahead.
Hi, thanks for that beautiful presentation. Unfortunately, I missed the first part, but I do have a question for you. On Tuesday, I believe it was, I had the wonderful opportunity to listen to, I think, your colleague, Faith Race, who gave a beautiful presentation also about sort of feeding behavior at your research stations. And I'm wondering that your results are really interesting. You showed that the number of visits were really important, right? The number of visits from the cows and the duration of length that they spent at the feeding bunk was really important. But putting those two pieces of work together, yours and Faith's, Faith noticed that some cows were being pushed away by other cows. So could it be that the connection of those two sort of phenomena explain each other? Or do we have to consider more than just time feeding at bunk without looking at the actual behavior of the cows themselves?
Yeah, so yes, I think because this kind of data, the social impacts maybe can be huge for us, right? That's why I emphasize feeding rate, but even feeding rate. So that's why we still working with those traits. For me, it's really amazing. And one thing that you want to do, I think I will do soon, because they're really interesting, is actually the latence. Maybe Faith talk about that. So latence maybe can indicate more things with feed efficiency and can explain more those questions that we don't know actually. Because if Faith study, it's really amazing, because there are like a lot of social impact when you put lactation, first lactation with third lactation, when it's just one group, when it's mixture group, maybe there is a huge impact.
It's fascinating.
And also with sorting, right? Because feeding rate, feeding rate is really high correlated with residual feed intake, but maybe there is some sorting. Maybe those cows is the other thing that you want to know. So those cows are the first one that go to the bunk. That's why it's more efficient. We don't know. yet.
So much more work to do. Keep it
Yeah.
up, Ligia. Great, beautiful presentation. Thank you.
Yeah.
Any other questions? I had a question. I was wondering, you found some of your feeding behavior traits to be correlated with some of the current measures they use for feed efficiency. Which trait did you think could be most realistically implemented on a commercial farm?
Yeah, I would say feeding rate, but feeding rate, we have the dry matter intake, right? The composition of feeding rate. I mean, there are some works that we can estimate the feeding rate in commercial farm using different technologies. So, but it still is under study, I guess. So then maybe duration, right? Maybe duration is easier, and duration is correlated with visit. So then, yeah. So like thinking about now, like implement now, maybe duration.
Yeah. Does your group at all study kind of these other technologies that can be maybe easier to use to measure the traits than the feed bins?
We have a professor here, João Doria. He works with this kind of technology, imaging and sensors. And yeah, they have been doing amazing jobs of prediction of dry matter intake and many other things.
Yes. Oh, interesting. Filippo, go ahead.
Thank you, Ligia, for your presentation. Appreciate. Thanks for giving us a update on what you're doing. I was looking at your correlation between first and second lactation, and have you considered, I mean, I think they're way too high, especially between first and second, given that the first lactation animal is still growing, and you know the feed efficiency is such a complex trait. Finding a correlation between first parity and second parity, which is even higher than milk production trait correlation, I find it a little bit too high. Anyway, have you considered that? What are what is your opinion on that?
You're saying about the residual feed intake on lactation?
Yeah, correlation between residual feed intake in first parity versus residual feed intake in second parity, especially.
Also for 1 and 3, right?
Yeah, but you know, the second lactation already is, you know, is just she's not growing as much, still growing, but I found it that a very high correlation, genetic correlation, that is even higher than milk production between first and second parity, for example, which is one of the energy sink that you're using to produce the phenotypic RFI, I guess.
This is a good question. I didn't think about, but maybe because we're modeling residual feed intake the way that we're just making like grouping the cows, so then we have compare cows that have similar energy sinks, for example, same cohort and same. So maybe our data is more. I mean, when I calculate
more homogenized, maybe.
I consider those. So maybe that's why. But it is a good question.
Thank you.
Yeah.
Flavio, go ahead.
Okay, can you hear me now?
Yes.
Okay. Ligia, thanks for presenting to us. I have a question. So you present all the results with your single trait model, then multiple trait model. And with the multiple trait model, you are presenting genetic correlations that are 0.79, 0.85 between the different lactations. So, but it seems that you are applying really repeatability model to analyze the residual feed intake, right?
Mm-hmm. Yeah, weekly.
So, but how comfortable are you with this? Because you know that the correlations are not very close to 1, right? especially including the third lactation there, based on your results. And when you use the repeatability model, you are saying the general correlation is 1. So I don't see how. I don't know if you.
Let me see.
I don't see a good justification for doing that. Why not use a multiple rate model if you know that the correlations are not very close to 1, and then you assume just for simplicity of the model?
But for using the multi-trait model for the residual feed intake,
Yes.
but I use bivariate model.
Pardon me?
I use a bivariate model because I would like to see the impact of residual feed intake in lactation 1 if it's different of lactation 2.
Yeah, no, I understood that, but you calculate the general correlations, right?
Yeah.
And they are not close to 1. 0.85,
Yeah, no.
0.79 is not close to 1.
No.
Right? You are going to find re-ranking of extreme animals. Not the overall re-rank is not going to change a lot, but if you look at the animals that are more extreme, the top animals, they are going to re-rank. So, but then you are using repeatability model that we assume that the general correlation is 1. Right? You showed the that's what I understood from your.
So why the repeatable model assume that the correlation is 1?
Oh no, that's it. That's the theory, right? Repeatability model assumes general correlation of 1. That's implicit in the model.
Because my idea, because we are using weekly records, so I didn't want to use a model that I have just one record per cow, because we're not doing this, we're doing weekly records. So if I'm using weekly records, I want to see the difference, not just about the genetic, but also I have to consider the difference among weeks, right? Because the first week would be different for the second, for the third. So then that's why I fit everything.
Yeah, no, but you could fit. Yeah, Nusha, but maybe I didn't understand well. What I'm thinking, you could have a multiple trait model, but within each lactation, you would have you have to consider that you have repeated records. It could be a repeatability model within each lactation, but between lactations being a multiple trait model.
Yeah, that's what I did.
So that's what you did?
Yeah, but I that's what I did. I did two things, but the second part, that's the genetic correlations that I present. So then I calculated the residual feed intake for each lactation as a different trait. So then residual feed intake for lactation 1 is trait 1, residual feed intake for lactation 2 is trait 2, and then lactation 3. So then I have a bivariate model. So then I use bivariate 1 with 2, 1 with 3, and 2 with 3, using repeatable model. Animal model, repeatable animal model.
Yeah. So, but so that was for the study. But what is the model that you are proposed to use? Like in practice, what the model that you are proposing to use?
You can use the model, the traditional model that we consider lactation for residual feed intake, but not nested. It's working, and we can use a model like a multiple model because the trait is the same. It seems there is no such a huge difference, at least. So then we can use the model that we are using, just consider the lactation, but not as separate traits. You don't need, for example, to use residual feed intake for primiparous and another one for multiparous and do all the analysis separate. We can do the same. I mean, I think are the same traits.
Just by including lactation as a fixed effect.
as fixed effect.
Yeah, but I don't know. But the genetic correlation is not really one, like or close to one.
You know, maybe there is an impact, like I said, of the number of cows. I don't have much cows on lactation 3.
Yeah, it could be. I didn't see the standard errors there.
Yeah.
Well,
No, it was not B. Yes, actually, the standard error of, I think, with lactation 3, it's higher. Yeah, there is in the paper, but I remember that I discussed that.
Okay, Ligia. So now I think I understood better what you did.
Mm-hmm.
But I can actually read the paper now to have all the details.
Because there is some rank, right? Even it's not that big, but maybe what is the impact of the rank? So maybe something like see the first, because I don't have much cow in 30 or for lactation, maybe just to do pruniperous and multiperous and see if like the impact, I can capture more the impact, if it's huge or not.
Yeah, and if you look at the rank of all bulls, usually with that genetic correlation, we're not going to see a lot. But you have to look at more the top, like 20 animals, 20% animals. Then even in your graph, you're going to see that you have more re-rank. When we are close to the mean, it doesn't change a lot, right? Animals that are close to the mean, and most of the animals are close to the mean.
Okay. Yeah.
Okay, thanks, Ligia.
Thank you.
Okay, so looks like we are out of time. So thanks everyone that joined us today, and thank you, Dr. Cavani, for the amazing presentations. We'll see everyone in 2 weeks, and have a great weekend.
Thank you. Bye.